Internal combustion engine with relation to thermodynamic might sound a little bit dull in many people's ear, but it's actually very, very important to at least have a basic grip of the thermodynamics in order to understand how power is actually developed in an internal combustion engine. As a starting point, I will go through the 4-stroke and the 2-stroke process. They are different, very different, I would say, and both processes could be applied on spark-ignited SI engines and compression-ignited engines. The next step after understanding how a 2-stroke and a 4-stroke engine is operated, we will jump into the PV diagrams and understand a little bit about the different processes behind how power is developed in this engine. And I can promise you, after going through this rather theoretical area, we will end up in both efficiency equations and power and torque equations. So keep on. There would be some important and interesting things at the end of this presentation. Okay, the basic 4-stroke process. It's the 4-stroke engine in general is creating 1 power stroke each second revolution. And the gas exchange process in a 4-stroke engine is also ending by closing the intake side. This is different compared to a 2-stroke engine, which ends the gas exchange process by closing the exhaust side. The importance with what part of the gas exchange which is ending the gas exchange process is the dependency of the gas dynamics happening either on air side or on exhaust side. So a 4-stroke engine is always more depending on what is happening on the air side, pressure wave wise in the gas exchange process. A 4-stroke engine also have a greater separation between air and exhaust side. In general, a 4-stroke engine is less depending on the gas dynamics from the external gas exchange system compared to a 2-stroke engine. The traditional phases, 4 of them, of course, it's a 4-stroke engine. The low pressure gas exchange cycle is defined when one of the valves are open. Obviously, when valves are open, the pressure in the cylinder cannot be so high. Gas exchange always starts with exhaust period, getting rid of spent air and fuel. And this is happening in the vicinity of the piston moving up from bottom dead center to top dead center, pushing out the exhaust gases. The intake stroke, which comes after the cylinder is empty, is happening while the piston is going down from top dead center to bottom dead center. And now the air inlet or the inlet valve is open. After we have filled the engine with air and fuel, we have the compression. The piston is moving up, increasing pressure and temperature in the combustion chamber, and in some point in time, close to top dead center, we fire the spark plug, we have a combustion, and we enter the last phase, which is expansion. For the 4-stroke engine, I would say most of the time, the gas exchange is controlled by valves, poppet valves moving up and down. And the poppet valves are operated by cams. The cam and the valves during the low pressure cycle do something like this. We have a valve lift. we have a crank rotation alpha. And since the exhaust is starting the gas exchange process, the valve lift looks like this for the exhaust valve and closes here. A little bit before exhaust valve closes, we enter the inlet period. So there is a period where both exhaust valve and inlet valve are open simultaneously. And that is called valve overlap. So here we go into the intake phase, and here we close. Since we are utilizing camshafts for operating the valves and the gas exchange in a four-stroke engine is piston position independent. Since the exhaust and intake valves are operated with a camshaft rotating at half the speed of the crankshaft, there is much more time available to create the gas exchange on a four-stroke engine compared to a two-stroke engine. On the other hand, opening and closing a cam-operated valve is taking much more time, so the utilization of the period with poppet valves is not as efficient as in a two-stroke engine. Any spark-ignited engine will operate compression, which is let me see now, 1 to 6, with a compression which can be described in a simplified manner as an isentropic process. The expansion after the combustion is also more or less taking place as an isentropic process. Between the compression and the expansion, we have the heat release. And ideally, the heat release in a four-stroke engine is happening isochoric at a constant volume, so a vertical line between 2 and 3. Coming down to bottom dead center to point 4, there are heat which is reacted also in a more or less isochoric fashion. A spark-ignited homogeneous combustion system is igniting air and fuel with a flame, which is propagating. This propagation of the flame can only happen if the mixture between air and fuel is kept at a very specific ratio, the air-fuel ratio. This means that when we drop down in power, when we reduce power of the engine, it's not only reduction of fuel which is necessary. In parallel, we also need to reduce the air amount. And since all piston engines are volumetric devices, the only way we could reduce the air mass rate into the engine is by lowering the pressure of the air, and that's happening by throttling. So in this case, in this PV diagram, after the expansion is done, we reach the throttle pressure conditions, which could be as low as 0.5 atmospheres, starting the compression from a very low pressure. That's happening in low load conditions. This is also creating pumping losses because air going through the throttle will also generate a power loss because the piston is now moving downwards in the intake phase, and that will take some power from the cycle, also reducing the efficiency of the engine. And we address that loss to pumping losses, or something called pumping mean effective pressure, PMEP. There is also something called IMEP, that's the other way around. That's where we generate power, and during the IMEP process, we have a clockwise rotating process in this diagram, where the work taking pumping loop is rotating counterclockwise. And both IMEP and PMEP will be contributing to the power calculation slightly later. Okay, not all engines are running flame propagation combustion system. We have the diesel engine, or a better name, compression ignited engine, CI engine, which in many cases compression and expansion is similar to the spark ignited engine, but the combustion is supposed to happen isobarically at a constant pressure ratio. The reason is that fuel is introduced directly into the combustion chamber while the combustion is still ongoing. So by matching piston movement in the cylinder with how much fuel is introduced, it's at least theoretically possible to keep the pressure during combustion at a constant rate. This means that power is controlled in a compression ignited engine only by fuel. We don't need to take any responsibility for air, because the combustion takes place in the spray where things are already taking place at a controlled air-fuel ratio. Because of this, the pumping loop in a compression ignited engine is much smaller, and this is one of the reasons that a compression ignited engine have better efficiency than a spark ignited engine. Okay, jumping now to the two-stroke engine. What can be said? Well, the two-stroke cycle engine delivers one power stroke every revolution. But as a kind of negative compensation, the two-stroke engine is not able to breathe by itself, neither inhale air and fuel nor exhale exhaust gases. So in order to breathe, create some gas exchange, we need a scavenge pump. And for this course, I am focusing on using the crankcase as a scavenge pump. So the crankcase is completely sealed off in a two-stroke engine, providing the scavenge. So inhalation of air and fuel, at least air, is happening here in the crankcase by a reed valve, or could also be a rotary valve, or in the simplest form also a piston control intake managed by the piston movement. Air and potentially also fuel needs to be distributed in the scavenging ducts up to the combustion chamber. So scavenging port and also exhaust port is controlled by the piston. And in the next phase, this pressurized air and potentially fuel is coming up to the combustion chamber, pushing out exhaust gases, instead of having the piston doing it, which is the case in the four-stroke engine. In the two-stroke engine, the gas exchange process ends when the exhaust port closes. That's why the gas exchange volumetric efficiency is strongly impacted by what is happening with the gas dynamics on the exhaust side in the two-stroke engine, and not so much for the air side. It's also true to say that the air and exhaust side is much more connected to each other in a two-stroke engine, simulation-wise, and because of a lot of reasons, the gas exchange process is much more mixed, much more complicated, both in real life and to do calculations on for a two-stroke engine. Yes, so that's basically the gas exchange processes for the four-stroke and the two-stroke engine. And now over to the PV diagram for the spark-ignited two-stroke engine. It's basically the same as on a four-stroke engine, but because the scavenging or the gas exchange is taking place more or less simultaneously with the compression and the combustion process, the events are a little bit shorter because the ports takes some room and some expansion and compression in the cylinder. The second difference is what's happening in the sealed crankcase, which acts as a pump. So we also have a PV diagram happening in the crankcase. Combustion. Combustion is maybe the most important of all systems, independently how interested you are of gas exchange and charging systems. Combustion can be made very, very complicated, but I choose to do it as simple as possible. So I'm neglecting combustion chemistry, for instance, how turbulence is created, and I try to explain the combustion with something called a heat release or even an accumulated heat release. So on the horizontal axle we have crank rotation as usual. The vertical axle would be how much of air and fuel is being combusted. So of course in the beginning nothing have been burned, so 0%, and hopefully at the end of combustion 100% should be burned. We have the top dead center here. The combustion always takes place as an S-curve, S-function like this. It could be a quick burning system like the dotted line here, or a more slowly burning system. That depends on the geometries of the engine and several other things. What is important for the performance and for the efficiency of the engine is that the 50% burn point should happen approximately 8 to 12 crank angle degrees off the top dead center. If we have a slow combustion system, to make this happen, we need to fire the spark plug a little bit earlier. But the goal is to obtain 50% burn 8 to 12 crank degrees off the top dead center. To make this happen, we control when we fire the spark plug. And the golden rule to save the engine from unnecessary mechanical stresses: always utilize the latest possible ignition point to obtain maximum brake torque. That will keep peak temperature and peak pressures at the lowest possible level in the cylinder, avoiding knock and avoiding mechanical problems with piston and crankshaft. Anyway, especially in high compression engines using maybe some kind of charging device, turbo, supercharger, there is a potential danger that the flame in the spark ignited combustion system is not able to light off air and fuel in the way we plan for. If the temperature and the pressure in the combustion chamber becomes too high, it can self-ignite and come to detonation. Detonation is a combustion process which is much, much quicker than the combustion we planned for with the spherical flame. And the gases which are farthest away from the spark plug is subjected for the biggest risk for detonation. Time is also a challenge when it comes to detonation and knock. So especially during low engine speeds in a combination with high pressure and temperature, the risk for detonation is highest. Detonation or knocking can be pre-ignition, where this detonation process starts before the flame is initiated, or more commonly post-ignition, when the flame has started to propagate, but some small parts of the gas is still detonating. During detonation, we hear a ping, ping noise, which is not so appreciated. That's the reason for the name knocking. And as can be seen on this piston, small local melting points can happen if knock is severe. And the reason for this is that the boundary conditions, the boundary layers, which acts as an insulation, is taken away with the pressure waves, the detonation pressure waves, when we have knocking. That's why we have local melting. The last mean effective pressure is the friction mean effective pressure. This cannot be visualized in the PV diagram because it's not related to the thermodynamics. It's related to the mechanical parts in the engine, creating friction. Friction comes from piston rings, from bearing losses, oil pump, water pump losses, and also the side forces created by the piston. It is engine speed dependent, but because of being dependent of the mean piston velocities. So that's why it's increasing slightly by engine speed, typically starting at the friction mean effective pressure of 1 bar and escalating at top engine speeds to about 2 bars. Two-stroke engines with ball bearings, not having camshafts, are normally significantly lower in friction mean effective pressure compared to four-stroke engines. Beside being average piston speed dependent, the friction mean effective pressure is also slightly depending on the peak pressure in the cylinder. Okay, now we finally have been discussing all the important mean effective pressures. So we could formulate brake mean effective pressure, BMEP, which is obtained starting with the indicated mean effective pressure, subtracted with pumping mean effective pressure, and finally also friction mean effective pressure. Torque from a certain engine is depending on brake mean effective pressure, which is the important part. And for a two-stroke engine, this is what torque you can expect it depending on the swept volume. This is the torque you can expect it from a four-stroke engine, and for the same swept volume and brake mean effective pressure, keep in mind that the four-stroke engine will generate half the torque compared to the two-stroke engine. Power is obtained by taking engine speed into account. Here you have the explanation of the different parts in the equations. And if you're interested in seeing how big IMEP is compared to brake mean effective pressure and pumping and friction losses versus engine speed, please have a look at this curve. So for the performance, but efficiency is also very important. And when you start with a PV diagram, everything is simplified. It's called adiabatic, which is a very nice word, telling that we neglect heat exchange. If we are able to keep the heat inside the engine, the efficiencies will be much, much higher. It's a complete lie, but it's good to lie sometimes because it simplifies things. So the theoretical thermal efficiency of a spark-ignited engine is actually only depending on the secondary compression ratio, the epsilon. And when you calculate that, it's amazingly high and very, very long way from reality. It's not taking the heat losses into account. It's not taking mechanical friction losses into account. And that is what's taken care of later when we come to the real the important fuel efficiency, which is sometimes also called the brake-specific fuel consumption. And when you recalculate that, compare it with thermal efficiency, is about half what you can expect from the theoretical thermal efficiency based on the compression ratio, or more correctly expressed, the expansion ratio of the engine. Okay, thank you very much for attending this pretty theoretical part of my course package. If you have remaining questions, please not hesitate to contact me at lennart.sander@boostbusters.com. Thank you for your kind attention. Bye.